Don't open the door. There's someone at the door.
Howdy.
We are HxMx, and this is our critical design review over our project map. So first we're going to go over the introduction. This is going to be the background, problem statement, con ops. Then we'll go into the project overview with the CBD, the functional requirements and performance specs, and the FBD. Then the technical presentation where we'll go over the electronic, software, and mechanical design. Then we'll show our demonstration, and then a project status update. So I'm Kinsey Sidness, I'm the project manager.
I'm Dustin Tish, the hardware engineer.
Jeremy Brennan, the software engineer. Shane Blows, the system integration engineer.
Our stakeholders, Dr. Joseph Morgan is our technical advisor, and Mr. Matt Leonard from T-Star is our sponsor. So just an overview of what's being done now. The main reason for our project is the delay in communication between us and the moon. It's about 10 seconds. The human mind is only can comprehend about half a second. So NASA needs to be able to train these operators on how to overcome that delay. So we have MALP, Mobile Analytic Laboratory Platform, and then a background over MALP. MALP was created 15 years ago by NASA, and we are trying to develop it into a modular platform for research. These operators will be using this to simulate control scenarios on terrestrial bodies. NASA has given the project to T-Star, which has given it to HxMx, where we'll be doing the controls and power management, interstellar communications, as they spoke about the communication, and then REACH is creating a robotic arm for this. This is to enable future projects on them.
So now we're going to go over the system architecture. One thing to take from this is the first multi-team project that any capstone team has done. So there is 3 to 4 teams working on this all at once. Over here you can see HxMx, which is us, and we're in charge of the vision, power, control, and maneuvering subsystem. Interstellar, like they said, is the wireless, the communication subsystem. REACH is on the sample collection subsystem. SumTech is working on terrain mapping, and then there is future projects such as collision avoidance and autonomy. So a problem statement. So T-Star needs a mobile robotic platform capable of emulating the movement and controls of a rover on terrestrial bodies. NASA has this 6-wheel rover mount, which you saw, and we will be implementing new technologies to assist in this training process. Our concept of op. So MALP will assist in the training of personnel on remote operations of rovers through user commands from NASA's JSC to various locations based on where they would like to test. So now we're going to go over our CBD. So here you can see MALP. This is how we receive MALP. It has the motor drivers and motors on MALP. So us, HxMx, we're going to provide the power. We're also going to create the queso board, which you've heard about. This will be sending HxMx controls to the motor drivers, which will then be sending PWM signals to the left and right motor. We have 4 physical e-stops on MALP. We then have 4 light bars on MALP. We have 2 cameras. And then we have a Pi with a 9-axis accelerometer, gyroscope, and magnetometer. And this will be communicating over UART to our queso board. We then have a local motion controller. And this is for HxMx, our demonstration of MALP, showing that we can control a robot. And then also the devices on MALP will be communicating over 802.3 to interstellar communication. They will then send this to the base station to show they are capable of moving MALP. So now we're going to go over the functional and performance specifications of MALP. First, we're going over the control and maneuvering subsystem. So first off, again, we're going to have a local motion controller. This is so we can show that we are able to demonstrate the motion of MALP. We then have a wireless communication system, which is interstellar communications, which is providing a wireless telecommunication system. It will be IP-based. We'll have private IP network addressing, a defined message format, such as UDP and TCP IP, and then it will integrate with our system to show that they are able to control MALP. Continuing, we will be able to monitor the position and motion of mount. This is through that 9-axis I was talking about, and it is a real-time configurable device with a 16-bit resolution, and you can see the different ranges that you're able to measure. Continuing on control and maneuvering. There will be multiple ways to control the e-stop on mount. The first one is through a button press on the controller if it's local or wireless. You then have if any communication is lost, and then finally those 4 physical e-stops on mount. Finally, mount. It is a chain-driven rover. Though 6 wheels, 3 on each side. Each side will have its own chain, so same speed, same direction. There's going to be individual motor controls, so this allows for differential tank mode, and we're expecting the speed to be 2 and 4 miles per hour. Going on to the power subsystem. So this system is battery powered. We're using 12-volt deep discharge batteries, and the user will have the capability of 12 volts, 24 volts, and 36 volts, and we are using 24 volts to power our motor drivers. We also will have power management, power monitoring, and voltage regulation on mount. We'll be regulating the 12 volts down to 5 and 3.3 at 5 amps, and then monitor the voltage and current at the 12 and 24 volt connections on the queso board, as well as the power planes on the queso board. Moving on to vision. So the imaging system on mount will be a consumer off-the-shelf technologies, and this will be implemented through a dual camera IP-based video system. And then overall, the system is going to conform to the system architecture that I talked about earlier, and this is through an interface control document that HxMx and IC are working on for future capsule projects and interactions. And then finally, the mount rover will have a cargo transport capability of weighing at least 35 pounds in the body of the mount.
Now we're going to go over the functional block diagram for our system. We're going to start with the system overview. So this is essentially the same as the FPD, or the CBD that you saw earlier. We have the battery input voltage that we're getting, the light bars, and the cameras on the left side. On the right side, we have our motor drivers that will be sending the signals to the motors. Below that, we have our e-stops. In the middle, we have our Raspberry Pi and our game controller that we will be using for the connected local control of the rover. And at the bottom, you see interstellar communications. Diving deeper into FPD, you can see the queso board here. We'll be taking the 12 and 24 volts in from the batteries. We'll be monitoring the voltage and current of both of those. We will then be regulating the 12 volts down to 5 and 3.3 volts, monitoring both of those power planes. The 12, the 5, and the 3.3 volts will all have output peripherals. We will have a JTAG interface. This is how we will program our microcontroller. We will have the motor controller block that will send the signals out to the motor drivers. And then we will have the breakout pins, which are for future projects. There's the peripherals that we have. We have Ethernet port to talk throughout the subsystem. And then again, the Raspberry Pi that we'll be using for the local motion control. That'll be powered off the 5 volts. Here you can see our voltage regulation. We take the 12 volts in after it's been monitored and regulate it down to 5 and 3.3 volts. Again, these are both at 5 amps. Here is our power monitoring for the system. Here you can see that we have broken the voltages up separately into 2 of each. We have the input at the top and then what we're actually using at the bottom. So any current that's being drawn on our board from these voltages is measured through our power monitoring devices, and these are I2C devices. Here's our Ethernet FPD. This is, again, how we're going to be communicating throughout the subsystem of mount. Here we have our JTAG interface, which is how we will program the microcontroller. And then at the top, you can see the UART connection of how we can communicate with the Raspberry Pi. Here's our motor controllers for the right side of mount. This will consist of a PWM signal and then 2 direction signals. Whichever one is grounded will determine the direction of mount. We can see the e-stop FET box here that we will dive into deeper later. This is for the left side. It's exactly the same except for 3 different pins of the microcontroller. Here's our e-stop section. So how the physical e-stops on mount work is that they're just buttons, and normally in a run state, they're closed circuit. When pressed, it opens it. So what we're doing is sending a ground to all 4 of these, and in our run state, we'll be getting that ground back, which will run to these 4 MOSFETs that are P-channel MOSFETs that a PWM is running through. If that ground is lost because any of those buttons have been pressed, it opens that MOSFET and doesn't allow the PWM signal to go through. to dive into our beta schematic. In the top left, we have our power inputs and the polarity protection for that. Below that, we have our voltage regulation where we regulate 12 volts down and 5 and 3.3 volts. In the middle, we have all of our power monitoring that we talked about. Top right is the power and ground pins for our microcontroller, and below that is the 12, 5, and 3.3 volt output connections. And here we have our Ethernet and our JTAG interface. Again, Ethernet is how we communicate, and the JTAG is how we will program the microcontroller. The bottom left here, you can see the two I2C lines. Those are the lines from our power monitors and how we will communicate with those. Here in the top section, we have our breakout peripherals. Again, this is going to mainly be used for future projects if need be. Below that, we have our motor control signals. This is essentially the e-stop section that you saw earlier. The PWM will run through those 4 FETs. If any of those e-stop signals are not grounded, it will open that FET and will not allow the PWM signal to go through. And now I'm going to show you the layout for our beta PCB. This is the top layer of our 4-layer board. Then we have our ground plane, our power planes that has 24 volts, 12 volts, 5 volts, and 3.3 volts broken up into the different planes you see there. And then we have our bottom layer.
All right, so now we're going to go over the software overview. We're going to go through the communication structure, the RTOS, the structure that I'm using, and then we'll talk about some flow diagrams for our controller input, PWM process, and then on our Raspberry Pi, the software we're using over there. So overall, we've got an Xbox controller in the 9-axis that we mentioned before, connected to a Raspberry Pi. That's using I2C, and then the Xbox controller is just a USB plug-in. So this is for our direct connection control over mount whenever we don't have an external connection over Ethernet there. That Raspberry Pi is then communicating through that switch and out and over to our queso board. The queso board is also in communication with the 4 INAs that are actually installed on board. That's why that's in a dotted line right there. And then the IP camera is connected to the layer 2 switch. And that switch is how interstellar is going to be able to communicate with any of these devices on board. So in our RTOS overall flow, so starting from the Xbox controller at the top over here, we're able to communicate out through that Ethernet out to the controller task. That's going to, to the UDP server. Yes, and then we'll be able to process that controller input and push that out to a controller data array. That array stores and then updates that motor update over there. Then from there, it's able to control those PWMs as well as some directional GPIOs. We've also included some additional functionalities like turning lights and kind of like an e-brake functionality with a button press. So from there, we have an interval-based voltage reading, right? So periodically, we'll be checking what the voltages are on those INAs, and as that updates, it'll push to a status array. That array will get updated, and then the status update is going to check the controller data array as well as that status array, take that data, push that back up to our UDP server, which will be pushing those updates back out the same in a reverse direction to whoever sent in the controller data will then get a status update as part of that process. So here, this is kind of a general look at our controller input. So as we step in, we'll pull in what that controller data is. We'll have to parse that because it comes in as that datagram. So it goes through, we have that broken apart because we've standardized the communication of those datagrams from between IC to ourselves. So in our test modules locally, we do that same communication scheme. So we parse that string, push that over, that data over to our actual motor update, and that's going to be able to take those values that we've been stored into those value arrays, pull out what it needs to know to update those motor PWMs and those GPIOs for the directional pins. On the Pi side, for our local controller, it's going to pull that data in the same data structure that IC is using. And then but before it actually pushes that out, it's going to first pull the accelerometer data. It's going to read through all of the 9-axis values that it has, process those, and then push that back out to the main controller program, and put all of that into a single file, push it out in an UDP datagram, and then it'll just start over. So it's constantly sending. So regardless of what the controller state is, whether it's trying to move or not, we're always getting controller updates. Here you can see the enclosure we'll be using. once we have fully installed this onto mount, we'll then put an clear acrylic cover on the top to just protect these devices. Our initial demo that we've done, we verified the voltage regulation so that we're actually processing that 12 volts down to the 5 and 3.3 volts, and we're getting the appropriate amount of current draw on those. We've also verified that we can do the local motion control. We had some initial push buttons to determine like various PWMs, and we were able to control those from the Xbox controller through the Pi over to the queso board, just to verify that our process was functional. And so in our most recent, we've updated those controls to communicate over that Ethernet, and now we are controlling those PWMs via the tank controls that are required, as well as we have the functionality to turn on lights and that functional brake as well. So in this next video, you're going to see I'll be able to use this Xbox controller to moving up and down on either stick will control one of the motors accordingly. So starting in the top right, we have the two motors that we have installed with a small H-bridge. That H-bridge is actually getting the exact same voltage PWM that we will be sending to the motor drivers on board mount currently. The red board in the middle is just our JTAG connection debug board. That's allowing us to connect over to the actual queso board, which you can see here in the top left. On the bottom left, you see the light we have hooked up, and then in the middle over there is our Raspberry Pi. So once he plays this here, you'll be able to see that we can control the motors via the joysticks, and then we can also turn the light on and off with those motors independently. And while they're running, we're actually able to then go through and stop the motors running once I figure out how to do it, and then we can stop it. There you go. It won't let those motors run while we're holding that button. As soon as you let go, you can. All right. So, and then as IC mentioned before, this is our full setup. Works the same way. They're just able to do it over a distance using their Colbys. Just go ahead and run that. It's the exact same video you saw earlier. We just trimmed it down just a teeny bit.
Okay, now the overall status of our project. Right now we are on time. We are expecting to do our final demo on April 13th and then sign off a week later on April 20th. Our labor budget, we are under budget. Total hours that we've worked so far is 369 hours, and we are budgeting about 1,052 hours to complete the entire project in 420. Our estimated remaining hours is 420 hours. So for materials, we are also under budget. Our SDP budget was $1,429, and our current budget is just $1,413. And then we've spent about $1,200 to the state. So major tasks that we have completed, we finished alpha, the schematic layout, and debugging of alpha. We have created the beta schematic and beta layout, and we have ordered the board and are expecting it sometime this week or next week. We have finished the alpha software, and then for testing, we finished the alpha testing. Most of the communication testing, we show that we can communicate with IC, motor validation, and the power management. So major tasks remaining is all of beta. We're expecting that to be finished mid-March. Hardware, or for final hardware and software, we're hoping by the end of March and early April. So that way we can do our final demo April 13th and sign off April 20th. So here's our timeline. Everything is on time. We are working on building the enclosure. We printed that today. And then our beta software is in the process. So here's our Gantt chart overview. As you can see here, everything's on time or ahead of schedule. So labor status in 419 as a team, we completed 471 hours. In 420, we are at 369 hours. as I said already, the labor estimate, we originally did 1280 and now we're down at 1052. With the estimated remaining labor, we are expecting 420 hours with 7 weeks remaining. That means we need to put 60 hours into each week. So financial status, looking at our SDP estimate to our current estimate, we're at $16 under budget. We have spent $1,200. Any questions?
We want to flip that first.
I have a question. I'm sure this wasn't part of the project, but I guess there's no means of monitoring the power usage and coming up with a power budget, determining that thing won't run out of gas?
So we are measuring the voltages of all the batteries on our data board, and we will be reporting that back. The user will just have to monitor that and make changes on changing batteries or charging them on their own.
But you're depending on the battery voltage to tell you how much is left.
Yes.
Okay.
Any questions from the NASA folks?
Dr. Evans, do you have any questions?
I kind of kept up with what you guys were doing when I was up there. You guys have done a nice job on this. I'm interested in the GUI that gives me system status. Have you got any demo of that from the software side?
So that's more of IC's project, and they demonstrated what the GUI would look like during their presentation.
Yeah, okay. So you guys are just providing the inputs to the GUI.
Yes.
I'm kind of following on your prior question about what resources do I have to monitor the availability of the life and status of the road as it's functioning.
So what's that?
Say that again.
Oh, life and status. I mean, yes, we have all of the 9 axes that will be telling essentially the orientation of the rover, and then we have the power monitoring that will tell you the voltages of those batteries and how much voltage is dropped from those and if you need to change them or not. Anything else?
Can you hear me?
Yes, sir.
Yes.
Okay. Will the GPS be providing me with a real-time track so I can monitor? Will it give me its own traverse plan?
So
as it's moving?
It will not actually have GPS. It will have the acceleration in angular and directional, but it's not going to be a GPS coordinate per se. That would have to be processed elsewhere. We're just taking from the case of the device itself, we are transporting that 9-axis data back out to the user so that they can implement that in the GUI. And then IC's got some ideas of how that can visually be displayed